Welcome everyone. Today we'll be discussing interpretation of batch reactor data. Before I start this lecture, I would like to review a bit what we discussed earlier in the next class. In the previous lecture, we have discussed the temperature dependent terms and also the concentration dependent terms of the rate equation. We have talked about single and multiple reactions, elementary and non-elementary reactions, and also discuss the molecularity and order of the reaction. We have seen how the rate equation of an elementary reaction can be written using its stoichiometry. About the non-elementary reactions, there is no direct relation between the order and molecularity. So how do we find the kinetic expression? So there are two ways. The rate equation may be suggested by theoretical considerations, or it can also be generated from curve fitting of experimental data. Irrespective of which method we use, the parameters of the equation, by parameters I mean the rate constant or the specific reaction rate, and the order of the reaction can only be found by experiment. So the objective of this chapter, the title of this chapter, let me write it down: Interpretation of batch reactor data. And what we'll be doing, we'll be looking into the process. So objective of this chapter, we'll learn how to determine the reaction order and rate constant, or also we call it the specific reaction rate from experimental data. So how do we do that? What are the steps involved? Before going into the steps, let's also talk about the process. So the determination of rate equation usually involves two steps. Step one. So we already know there are two terms in the reaction rate equation. One is the concentration dependent term, and the other is the temperature dependent term. So the first step is to figure out the concentration dependency. So we have to find out this at a fixed temperature. So basically we fix the temperature of the experiment, and then we conduct a series of studies to figure out how that rate varies with changes in concentration. And when that is done, we move into the temperature dependent term. So this is followed by experiments at different temperatures. So basically the part one or step one is repeated for several temperatures, and usually using the Arrhenius equation, we can figure out how the rate constant varies with temperature. Okay, now moving into the So these are the steps, but if first we'll be looking into the concentration dependency. And since there are experiments involved in the process, first question um, that probably comes to our mind is what type of equipment do we need? So usually the equipment by which this empirical formulation is obtained can be divided into two groups. One is batch type of reactor, and the other is flow reactors. You are probably already familiar with both these types of reactors. Batch reactor is simply a container to hold the contents while they react. In the flow reactor, usually there is a inlet. There may be more than one, and then we have the outlet. At steady state, the inlet and outlet flow rates are equal. However, as we have seen, the title of this chapter is Interpretation of Batch Reactor Data. So during this discussion, we'll be focusing on batch reactors only. The reason batch reactors are very suitable for homogeneous reactions, and we are concentrating on homogeneous reactions at this stage. And these are usually operated isothermally and at constant volume, and simple device, so suitable for a small scale laboratory setup, and it doesn't need much of instrumentation. So maybe temperature measurement, and in some cases pressure measurement is good enough. So this is why and whenever possible we use the batch reactor for homogeneous kinetic data determination. So since we talked about the equipment, now we also need to know what kind of data we are looking at. So data we are talking about so if we remember the rate expressions something like this. So the rate expression, and we are talking about the concentration dependent part only. So usually depends on the concentrations of the reacting species. So definitely our first choice would be to follow the concentration of a given component. And this is usually um, the rate limiting reactant, but we can also do the same for the other ones and then find the concentration of the limiting reactant using some equations. There must be some relation between the concentrations of the reacting species and the products. In some cases, we can actually measure some other physical properties of the reacting fluid. For example, it may be other properties. A few examples, maybe electrical conductivity or refractive index. There may be many other, but these are very useful at times. We may also look into the total pressure at constant volume systems, constant. So this is useful if we have uh, changes in number of moles for gas phase reactions, then the impact of the reaction can be easily realized by change in uh, the pressure. And if we can use a constant pressure system, then we may look into the total volume of the system. Now, let's say we have the data. How do we process this data to find our rate expressions? So there are two methods. There are two categories of methods. One is known as the integral method. So what is this integral method? In this method, we initially guess a particular form of rate equation. So let's say we have a reaction like this, and we start with a guess that this is a first order reaction. Then in that case, the rate expression will be something like this. If we, in such a case, if we integrate this equation, it's in differential form. So for first order, there will be a linear form of equation, and for the second order, we'll have a different equation which will give us a linear uh, form. So first we guess the form of the rate of equation, and then we figure out what will be the linear form for that particular uh, order of reaction, and then we try to fit our experimental data according to that equation and see whether it's a straight line or not. If it is a straight line, then we assume that our assumption of the order is correct. If it is not a good fit, then we make a second guess and continue with the same process. So maybe then we move on to order 0 or order 2 and try to fit our data in that linear form and see whether the experimental data matches with the prediction or not. So this is an iterative process, and we have to keep uh, doing it until we find the correct order of the reaction. So definitely this may sometimes need extensive amount of work, and if you are dealing with a reaction which has a fractional order, then this may be an issue. Um, but there are ways to deal with that. We'll have a look at that when we discuss further later on. Okay, the other method is known as differential method. So in this method, we fit um, the experimental data directly without performing any integration. So we see the rate expression is already in a differential equation form. So if we take a logarithm of the entire thing, it basically becomes a linear equation, and we try to fit uh, our data into this equation, and say if the order of the reaction is n, which is not known, so in that case, this equation becomes like this, and this becomes, so from the slope of the reaction, we can figure out the order. So even without knowing the order, differential method will give us the order of the reaction. The problem we have is with this term. So from the experiments, we do not get dCA by dt. Instead, we measure Ca or some other property which is related to Ca. So in that case, we have to calculate this differential value. So dCA by dt has to be calculated from the experimental data. Now, it seems the differential method is much, it involves a lot less work, and maybe it should be preferred all the time. Okay, the um, the thing is, when we use differential method, we are not using the direct data we get from the experiment. And if the accuracy of the experimental data is not good, then that error actually amplifies when we calculate this term. And this eventually leads to more error in our fitting, and it's possible that we end up with wrong order or specific reaction rate if we always follow this method. So definitely differential method involves less work, but we have to make sure that the experimental data we'll be using for this method are accurate. Otherwise, we may uh, end up with wrong results. So, on the other hand, integral method is simple and easy. It's just repetitive work. So, if we are unsure of the order, or if we already, maybe in some cases we can guess the order from from the order of the similar uh, reactions. In that case, we usually start with the integral method, and we test the data for specific orders, and we try to match those, and by approximation, if our approximation fits the experimental findings, then we say, okay, this is good enough. And even with inaccurate data, integral method is more likely to give you a good result. So that's why usually we go for integral method only, um, unless differential method is really required. And you will be doing the same for your 402 experiment when you do the kinetic study of esterification reaction. Now, okay. Now, as I have mentioned, we are focusing on batch reactors here. Visualizing a batch reactor is very easy. It's just like a beaker. Maybe not open to the atmosphere, but even if it is open to the atmosphere, we can call it a batch reactor. So this is fine. Um, However, the batch reactors can be uh, constant volume and also um, variable volume. So first, let me give you an example like uh, so constant volume. So batch reactor is a constant volume reactor when it has fixed boundaries. So the walls are fixed. On the other hand, variable volume batch reactors will have moving boundary or boundaries. So the walls are not fixed. For example, if you conduct a reaction inside a balloon, then that balloon is the reactor, and depending on whether the reaction um, is so by the reaction, if the number of moles reduces, the size of the balloon will go down. If it's an expanding reaction, then the size of the balloon will increase. So this is an example of a variable volume batch reactor. Another good example is the piston type of reactors we have inside a car engine. So the piston moves at different stages, and uh, hence the reactor volume also changes. So initially we'll be focusing on constant volume batch reactors only. So we are familiar with this equation. Okay, and so here V is the volume of the reactor, and we can write it like this: dNi by V dt, and then this NiV over V is basically dCi, the concentration within the reactor. So this is how the concentration is related to the rate of the reaction. Okay. This concentration, if this gas phase reaction, and for ideal gases, we can also write Ci, and then our rate expression becomes so for gas phase reactions, by measuring pressure, we can easily calculate our reaction rate. We do not need to always measure the concentration. Now, let's look into the two reaction progression variables we discussed earlier. One of them is the conversion, and the other is the extent of reaction. So let's use the symbol Xi for conversion. So conversion is given by the number of mole changes by initial moles present for any particular reacting species. And this can be written as Ni equals Ni naught 1 minus Xi. For a constant volume system, this becomes, for constant volume system, so the volume of the reacting fluid is not changing. So it's V all the time. And so this becomes Ci equals Ci naught 1 minus Xi. Let's look into this other reaction progression variable, the extent of the reaction. So the extent is defined by this equation. So here Ni can be written as Ni naught and Ci is then for constant volume system again Ci naught extent by volume times stoichiometry. So when you do the kinetic study and subsequent kinetic analysis, here in the equation we have Ci by T. We can use that form. We can also move to the other form, conversion. When we use Ci as the independent variable, probably we'll be looking into extent, and when we use the conversion, Ci is no longer in the equation. Instead, Xi is the independent variable. So we need to know the conversions at different stages, and from there we figure out or we do the mathematical calculations and then use those calculated data to figure out the order of the reaction. So as we are looking into the integral method, let's start with um, a specific type of reaction. So we'll be looking into different orders. Let's start with irreversible. So we are assuming the backward reaction is negligible. Unimolecular first order reaction. So let's assume a reaction like this. A is the reactant. From there we have some products. It may be one, it may be multiple. So it's an irreversible unimolecular first order reaction, and for these the order is 1. So and here from here we can write it like this. For the first order it's very simple. We separate the variables. We don't need to go into the extent. Since it's a unimolecular reaction, we can just keep using the concentration of Ca. So after the separation of the variable, we do the integration. And from there, we get this integral form. We can also use this type of equation, or I should rather say, we can use conversion for finding a linear form for this type of equation also. So as we have seen, Ca is basically Ca naught times 1 minus Xa, where Ca naught is the initial concentration of A and XA is the conversion of A at any particular time. So in that case, dCA by dt is basically CA naught dXA by dt. So if we put this here, this becomes CA naught minus dXA by dt equals negative KCA naught 1 minus XA. So overall equation after eliminating the common terms becomes K1 minus XA. Again, we separate the variables and integrate from 0 to XA. So 0 was the initial conversion at time 0, and at any particular time t, the conversion is XA. So the linear form becomes ln 1 minus XA kt. So now we have two equations, and we can arrive at the other form from one from the other very easily. We just need to put the equation for CA in terms of XA, then we get the other equation. Now, what do we do with these equations? Say, we have done a series of experiments for this reaction, the reaction we just looked into, and we have, say, data of this form. So 0, say this is CA naught, say T1, we have CA1, T2, we have CA2, now the linear forms of our equation in terms of concentration, the first one, and in terms of conversion, the second one. So what we do, we simply take the experimental data and calculate our, so this can be rewritten as on CA minus on CA naught KT. Or maybe also if we want to make the other part. So these are linear equations. If we plot ln CA by CA naught versus T, and we have the required data here. So we just need to figure out what is our ln CA by CA naught. So CA naught is this. So initially this will be 0 since CA by CA naught is 1, and then we'll have other values. So we plot T against ln negative of ln CA by CA naught, and we say if we get some data points like this which fits to this straight line, then we can say our order of reaction is 1. and here the slope is nothing but our K, the specific reaction rate. And I will get the same when we plot negative ln 1 minus XA. To find XA, we'll be using the equation for XA, which is so we need one more column here, and we can calculate XA, and from there we can also test whether we get a straight line or not. So either will do. So if our experimental findings or experimental data fits with this straight line equation, then we can easily say that the reaction we are dealing with is a first order reaction. Okay. Now let's look into this irreversible bimolecular type second order reaction. So moving from first order to second order now. And here, say we are looking into this reaction. Okay. And for this case, we are also assuming a number of things. Why? Okay. So when we discuss the next reaction system, I'll come back here and then answer to this why. But let's just remember for now that for this case, CA0 and CB0, they're not the same, and hence NA0 and NB0. So the initial concentrations of A and B and mole numbers of A and B, they are not the same. Since this is a bimolecular second order reaction, so the order is 1 for each of the reactants. So the rate expression is something like this. Now, what about CA? We are going for, so in this case, we are not going to use the concentration as the independent variable, rather we'll be using the conversion. So that makes our life a lot easier. So this equation we already know for constant volume systems. What about CB? So CB is nothing but CB naught minus conversion of B, which will be CA naught times XA times the stoichiometry of B. Here the stoichiometry is 1, minus 1 for both, so that's why this is CA naught times XA. Now, if we take out CA naught from this equation, we can write it like this. And then So here MB is nothing but the ratio of initial concentrations of B and A. The reason we are doing it like this is to put both the concentrations of A and B in a similar form. So if we look into the concentration equation for Ca, here we have Ca naught times Ma minus Xa, where Ma is nothing but Ca naught by Ca naught. That's why it's 1. So all the concentrations we are trying to uh, bring them in a similar form. So from here, this becomes now. How do you move forward from here? So we also replace this Ca with this equation here. So eventually this becomes Ca naught dxa by dt and now again what do? We separate the variables and integrate. So we bring all the xa terms on one side and the limits are for time 0 conversion is 0, for time t conversion is xa, and here if we integrate this we get we can also have some other forms of this equation. Okay, for example, this mb minus xa times mb1 minus xa can be written as cb naught minus ca naught minus xa. If we simplify this, this becomes the top part of the equation is nothing but cb. So what we are doing, we are just doing some mathematical manipulation here. And so this can be written as cb by cb naught, ca naught by ca. So we actually found several forms of the term, um, the logarithm term. So the equation can have many forms. If we summarize this, this will be equal to Ca naught Mb minus 1 Kt. So we take either this, or this on the left hand side, and then this is what we have on the right hand side. And we must remember Mb is not equal to 1, the condition I mentioned at the very beginning. So if Ca naught and Cb naught they're not the same, then Mb naught cannot be 1. So we have to remember this. So in this case, we can plot any of these. So if we look in here, Cb and Ca, these are variables, but Ca naught, Cb naught, these are constants. So we can either use this or this or this to plot. Let's have a look. So if we plot ln Cb by Ca, and if our experimental data fits with this expression, our intercept will be ln Cb naught by ln something like this, and our slope will be Ca naught Mb minus 1 K. So here again from the slope, we'll find out the specific reaction rate. I think with this, we'll conclude this class. We'll continue um, from here in the next class, and please remember the reason for this inequality. We'll discuss this in the next class.